In the previous section, we described the components of a LabVIEW FPGA system. By the end of this module, you will be able to describe the differences between a LabVIEW FPGA system and an DAQmx system. To understand the paradigm of a LabVIEW FPGA system, it's important to understand the specific components found in a traditional measurement system. So here we have a DAQmx system, and if we take a look at it, we see that the M-series device, that's vendor defined, right? This is a piece of hardware that you're not defining the functionality of the hardware. This is something that the vendor, namely National Instruments, in this case, has provided to you already. There's also a driver, so you see the DAQmx driver, and this is also vendor defined. It's the way that your hardware communicates with your software. And then what you do get to define in this case is your LabVIEW VI. So here you're able to define the software that executes on the host PC. So if we take a look at the LabVIEW FPGA system, let's kind of contrast that. So let's take a look at the hardware side first, okay, on the right side of the slide. So the real hardware that you're buying, of course, some of it is going to be vendor defined. However, because you're able to actually program the FPGA chip, which is hardware that exists on the real hardware, you're actually able to define the functionality of the hardware itself. Now, if you take a look at the software side, there's still a vendor-defined NI-RIO driver to communicate between the hardware and the software. But you can also, again, define something on the host side. So on the host PC side, you can create and define how that host program works and how that host program is going to communicate with your customized hardware that you're also defining the logic of on your hardware. In this slide, we see how decision-making is done in software. So if you look at a traditional system, notice that you've got your UUT, your unit under test, and you have all these layers between the hardware and the actual calculation. So if you take a look at it, you've got your UUT there, and it's got to go through an I/O layer. Then it has to run on an operating system, and then it has to go through a driver API, and then your application software, which you're defining the calculation on. Now, if you're running this, a crash can occur either at the OS level, at the API level, and also at the application software level. So there's several places for a crash to occur. Also, if you're running this on a Windows OS, you're going to get response times in the range of milliseconds. If you're running it on a real-time OS, you get some better performance. You can get things in the range of microseconds. However, there's a lot of, because both of them are running on OSs, there are many places for that crash to occur. So here we contrast that with decision-making in hardware. So if you're looking at a LabVIEW FPGA system, you've got that same unit under test. However, that I/O is going straight to your FPGA, which is implemented in hardware. So if you look at this, all that calculation is being done on the hardware. And you notice that the operating system, the driver API, and the application software are not involved at all. So here we see that we can have the highest amount of reliability, and also you get to execute things in the range of nanoseconds instead. So it's much faster and very reliable. Here we see a couple of examples of LabVIEW FPGA applications. So one thing you can use FPGA for is intelligent DAQ. So if you're using FPGA, you can have customized timing. You can get faster speeds and synchronization. You can create custom triggers that can trigger off of multiple lines, analog and digital. You can also have a lot of custom counters. So you can implement that counting however you want because you're defining that in hardware. You can also have multiple scan rates. So for example, you can have multiple rates getting analog input, but you can have each of those loops running at a different rate. Also, because it's FPGA, you get ultra-high speed control, so you can get things in the range of nanoseconds. Because you have fast speeds, you can have specialized communication protocols that you implement. Also, if your host computer is spending a lot of time and has a lot of CPU-intensive processing, you can move that down to the FPGA, so that way the CPU isn't as taxed. Also, complex timing and synchronization, those are all possible on FPGAs. And another use case is doing hardware-in-the-loop testing. So because of the reliability and speeds of FPGA and the determinism of it, you can also simulate things like sensors or protocols and things like that by doing HIL testing. Now you can describe the differences between a LabVIEW FPGA system and an DAQmx system. Next, we will describe the LabVIEW FPGA architecture on Windows and LabVIEW FPGA architecture with LabVIEW Real-Time.